Hi, my name is Jan Brugard. Today I will present 3 different cases from industry and how they have used SystemModeler in 3 completely different applications. One from helicopter landing, one from precision medicine, and one from producing clean energy. Thank you. My name is Jan Brugard, and well, I have I think the toughest schedule, like 9 a.m. today is kind of tough, and then the last one today is also a tough one to have because kind of people tend to want to sleep this Friday morning for some reason. Anyways, I'm going to present on SystemModeler in industry. The idea is to give an idea of how you can actually use SystemModeler and the Wolfram language to solve real use cases. So I won't do you won't see like any lines of code or things like that. That's not the purpose of this, but hopefully you will see what type of things you can accomplish with the software. And it's based on work that has been done by consultants that we have. So it's Mikael Forsgren, Marcus Dahl, Håkan Wettergren, and then, well, I'm there because I'm taking the credit by presenting. It's actually the same case. I was presenting education before, and I hadn't done the work. Present the WCM new in SystemModeler. I didn't do the work. I just take the credit. That's my thing. Okay, so let's start with this. So SystemModeler is used in a wide variety of areas, which is both good and bad because sometimes people don't really identify themselves with it, as it can range from things like a fighter aircraft to medicine. And because behind the scenes, all these things can be described in differential algebraic equations. And if you only look at the math, it's kind of the same. It's just that the x represents something else. Happens to represent temperature in one case and, let's say, velocity in another case. And what I will do, I will show examples from 4 different companies. Cybero, they're doing that drone up there in the middle. And I will show a project where they try to design a landing system so they can land autonomously on a ship when there's heavy waves. Then I'll show an example from a company called Clean Energy, and you can guess what they are doing, what the type of things they're doing, clean energy. And then we have the CMIV, which is a research group in Linköping, where we are based, and AstraZeneca, a pharmaceutical company that are using SystemModeler for diagnosing or estimating liver function. And I'll come back to why that is important. So 3 completely different cases, but all of them I will show have the same solution to reach their goals. They're using model-based design with the Wolfram Modeling and Simulation Suite, meaning combining SystemModeler and Wolfram language. So let's get started with the first one. Okay, so Cybero, what are they doing? Well, as I said, they want to land autonomously with drones on a ship in rough sea. And how would that look like? I will show a YouTube video. Don't bother really about the sound. You might. So now this is not from their helicopter because it didn't really when we started with the project, it wasn't landing yet. That was our thing to simulate and try it. So this is the kind of conditions you're supposed to be able to land on autonomously. And we will see here a helicopter coming in a while. The helicopter has a pilot, so that's also kind of course, a bit tricky. But the benefit the pilot has, let me just turn down the sound a bit, there like that. The benefit for the pilot, of course, is that he can see the sea, for instance, and he can see the ship. So he can react to what he's seeing. But still, you can kind of realize that this is a pretty tough thing to kind of manage, right? So let's just skip forward a bit. I think around here is where he finally manages to land. So he has this guy telling him, well, okay, now try, go. And it lands and connects to the ship. Okay. So then let's go back to the Cybero scenario. They want to do this autonomously, as I said. And basically, they are doing, this is done in 4 steps. They have a landing algorithm where the helicopter has been out there, or the drone has been out there doing some surveillance. It's for surveillance of the border, basically, the border here. So it's standing there saying, okay, I'm ready to land. And then an officer or the captain, someone has to tell, okay, get ready to land. So then it goes to something called touchdown standby point, where it has to wait for a bit for everybody on deck to get ready for whatever they have to do, and then to tell it, okay, now start doing your things automatically. So what it does then, it goes to a hovering position, which I think is about 10 meters above the landing plate. So it's standing there and trying to find an opportunity where it can land. And of course, it can't see the waves, but what it can do, it will get measures of the current movement for the ship. And based on those measurements, it has to guess when it's a good time to try to land and which angles and so on to do that. So eventually we'll try to do that, and it lands. It's pretty nice. So what's the challenge? Well, when is it actually safe to land? That's the big question, of course. And how do we test this without crashing hundreds of helicopters? They're pretty expensive. Because you can be pretty sure that your first attempt at developing a control system will not be perfect if you just develop it and try it. So then what happened is we got to develop a model for them. And the model looked like this. We developed a library where you have a model of the ship and actually of the sea conditions. So kind of we model all the seas in the world. And you have the drone up there. And yeah, this is basically illustrating the command you get from the ship. So you have all these. And then they sent to us the real controller, which was implemented in C code, developed by a company in Switzerland. So we got that one. And then we could plug that into our model, use that, and then design a landing algorithm, and also implement the landing algorithm we had. So using that, we could start to simulate the system in different conditions. So at this point, here was doing things in SystemModeler. At this point, we start to use the Wolfram language to generate different scenarios with this controller. Try to land, try to find a way to calculate like a landing window for them. Iterating, making changes until it actually works. It turned out that the control system they had to begin with, it would kind of crash more than half the times would have been a crash. So like, it was kind of important to do some testing before you actually went doing it. So the things you could see was we could calculate, and this is not real data, we're not allowed to show that. But basically, based on the movement of the ship, we have developed an algorithm that detects landing windows of opportunity, basically, for the helicopter to try to land. So it says, okay, from this time on to this time on, we predict that the sea condition will be, or basically the movement of the ship will be nice, and you have the chance to land. So now take a try. And it starts to try, and it might have to abort if it gets a warning signal back. But if we do a bad estimate, and then we don't have time to, for instance, if we would try to land here and suddenly we have this ship movement, we will crash into it and fail. So then we run a bunch of scenarios, and can I make this bigger, like that? And what you see here is basically, once we've run here 0 to 180 degrees, it says, it's how the ship is positioned in relationship to the waves. And these curves here show basically, so we have waves that have a 150-meter wavelength and 4-meter heights on average. And then there's a kind of stochastic process. And then we can see here, on this scale here, is how much the ship is tilting at every point when we're actually landing. So we're performing simulations, and we can find out that the median of these landings will be within this kind of area. And what we know is that if it's less than 7 degrees or something like that, then it's safe. But it turns out that for some angles here against the waves, the maximum tilt for the vessel is pretty big. So that's, of course, terrible. So it tells us that, OK, if we're actually on, we need to be within these angles here to be safe, and with these angles. Because in these angles, there are chances that we will get too tough conditions to be able to land. And based on that, we can then, and I'll show this very quickly, we can then do a simulation and see how the helicopter lands. Let me just kind of skip here because I will be tight on time. OK, so it aborts there. Let's actually up forward. And then it lands. So basically, that's what it does. And it turned out to be very successful at the end. OK, so that's one scenario. Next one. And it's clean energy. So their goal, to create clean energy. How do they do that? With a so-called concentrated solar power system. Does anybody know what that is? One. That's good. I never heard about it before. So this is basically how it works. You have a big parabolic dish that concentrates solar power into a cavity. And so that cavity becomes hot, of course. And that heat is used to power a Stirling engine. The Stirling engine then is connected inside the box you see there with a kind of, it looks like an N, kind of. That's where the Stirling engine is, and then you have a generator. So that is connected to the generator, and then the generator generates the electricity. So that's the basic concept. So some challenges that clean energy had was they wanted to know where do they have the biggest loss of energy in the system so they can optimize it. What part should be modified for maximum profit? What is the predicted profit of X number of dishes in place Y with weather Z, and so on. So they have plenty of different questions that I wanted to answer, and also things like how would a specific system work on a specific location. So yet again, what they did, together with us, they developed a model in SystemModeler. So the model contained the parabolic antenna, the kind of, and here is kind of, we'll have the cavity that will be used to heat the Stirling engine that then connects to the generator. And then some surrounding systems around that, like cooling systems and so on. So they do this. Then they can synthesize the controller, just as we did with the clean energy or with the Cyber project. They simulate the system and can test scenarios like, OK, what if we move this system from Australia to Dubai? How will it work? Can we make changes so it works better in Dubai than it would do otherwise? And in this case, they only need to change weather data, of course, and apply it on the same model, and they'll see how it works. And then they make changes, iterate, and learn from that. If we look at the results, what we see here, the blue dots correspond to measured signals from operation. The green dots are simulations of the same. So you can see that the relationship, and what we see is power output. So the estimated power output from the simulation is following pretty well the actual output. There are a couple of outliers there in the operational output, and there are probably measurements, so probably the simulation is more accurate than the measurement in that case. And then they have their own kind of metric for that kind of makes some kind of relation between the power and and their and the solar like parabolic antenna that would have the quote of that and to see it in nowhere. But you still see it's like fiction. So meaning they can trust the results. So when they do a change, when they move it and test what happens, as I said, in Dubai or in Australia, they can trust that this is actually what's going to happen. So now they can start fine-tuning. If they want to increase power production, for instance, they can try to see, can I change the controller a bit? Or can I fine-tune the heating system? Or whatever they need to do to accomplish whatever the kind of goal is. Okay. So, final example. So liver diagnosis. AstraZeneca and CMIV are both developing methods to diagnose. Oh, this is actually from another person. Let's remove that. To diagnose liver condition. The thing is with liver condition is that there's no good way to measure that today. And about 5% of Americans, for instance, have bad liver condition. So it's a pretty big issue, and there's no good way of getting that, how the liver is actually functioning. So, of course, you want to do this. And for you, those of you that don't happen to know what the liver is, it's much bigger than I thought it was. And probably you guys have better knowledge about anatomy, so you would know that, how it looks like. But anyways, what they do is they use MRI scans for this. So they put a person into an MRI scanner. But before that, they let them take a so-called contrast agent. So they take this contrast agent that will then kind of be transported through their body, so through the bloodstream, into the extracellular space, into the liver cells, into the bile, and so on. And it's called contrast agent because when you pass it through the MRI scan, you will get changing colors depending on how much you have of this specific agent over time. So here we can see a time series from 0 to 30. And we can see that it goes from very dark, corresponds to how much of this contrast agent we have. So now, okay, that's fine. We know how some transported, but how do we know if this result represents a healthy or an unhealthy liver? That's the important question, of course. That we can see that, okay, this took 30 minutes to reach this, or 45, doesn't tell us anything if we don't really know if that relates to healthy or unhealthy liver. So what they did, again, together with us, with Mikael in this case, was to model of the entire system with the liver, the bloodstream, and the one. And you have the infusion there of the contrast agent. Well, you don't really do that with a needle, but anyways. Then you calibrate the model with different conditions, different measurements you've done on in this case, AstraZeneca has done it on rats, and CMIV on humans. So the model works for both. And so they calibrate that in the Wolfram language to get it to run. And then they run an MRI scan and match a simulation with whatever they can see from the images. So basically using image processing in Wolfram language of the MRI scans, they can map that to parameters in the model. And I'll illustrate what kind of results they will see. So these are the things they will see. So what we're seeing here are two different models. One, which was the original model, the blue one, and then the simplified model. And we can see that show very much the same result. And the are the measured contrast from the MRI scans. So we can see in this case that what we measured corresponds to the simulations of a normal functioning liver. And if we look at the slightly reduced function, of the liver. This might look like this. We see a good correspondence again between those. And if you have severely reduced, there's something else. So basically, by taking these MRI scans and correlating that with simulations, they can see which type of problems they have. Now this works for a liver as a whole, but the interesting thing with the liver is actually it's consists of several kind of compartments, and one part of the liver might be perfectly healthy, while another might be unhealthy. So next step is to try to do it so you can actually see which part of the liver is malfunctioning or actually functioning well. So if I end up this by showing it together with our scan here, we can see, let's play that. You can see here how it changes color, and that's basically what we have then correlated to these dots are corresponding to the color that we see here. And this is from a rat, by the way. So in that way, they can now tell if this liver is in good condition or not, so the doctors know if they should take some action or not. Okay, so what's my conclusion to this? Well, 3 completely different examples from different domains, different problems. All were tackled with the same, meaning model-based design. So using a model and testing different hypotheses in the Wolfram language, they could solve really tricky and for me, kind of really interesting and problems. So the question then is, what could you accomplish with model-based design? So with that, I thank you very much. And before that, right after this, there's a reinforcement learning with SystemModeler presentation, and there's a hardware lab downstairs where you can do a bit of SystemModeler. Thank you very much. Any questions? I have 2 minutes.
Talk about like the new version 5.0.
Yeah, that was we had that yesterday. So the new version 5.0, if I would say very briefly, what we've done is a first important step to make it even more integrated with Mathematica. So which you can see if you go to the web pages nowadays, we don't really separate which parts are done in Mathematica or which parts are done in. Before we presented, this is done in the SystemModeler interface. This is done in the Mathematica interface. Now we're all looking at what type of tasks are you modeling, are you simulating, or analyzing, and then whether they are in SystemModeler or in Mathematica. Doesn't really matter when you present it because we see it as a whole. And a lot of what we did was doing those kind of steps. So you will see the 5 series will do a lot in that direction. And there was a presentation yesterday on the Wolfram language integration, which is part of that. So what will happen is that SystemModeler will work right. If you have a Mathematica installation, you don't have a SystemModeler, you will be able to run simulation. If you get the model from someone, you will be able to run it in Mathematica without having SystemModeler and doing all the analysis without having that. So meaning if you're developing a model and want to give that to others for them to play around with, you can do that even if they don't have a SystemModeler. So it's like a deployment for end users of your models, consumers of your models. So that will mean that so that will first be on the desktop, and then will be part of the Wolfram language on the cloud and so on. So it gives a better workflow for you when you want to kind of interact with others. But then was a bunch of other things like that are. But there's a presentation, and I think you can see these presentations online afterwards, right? Or you can get the material at least, I think, on Pathable. And of course, you can go downstairs, and I'll give you a bit more of a presentation.